all know Ken, who has agreed to be recorded apparently.
Yep, I did.
How we do this?
So Ken
Like to work on a variety of problems. Today we're going to hear about some quantum computing problems.
Yeah.
Or hopefully solutions.
So yes, a problem. The goal here. Actually, before I jump into this, I've had a couple people ask me about there's a Google announcement about their new, I think it's Willow chip. And the thing that's interesting about it, the advance they made, it has to do with something called error correction. And just like in the computer or your laptop, you know, when you store, say, 32 bits in a word, there can be cosmic rays, things like that, flip a bit. So what we do in ordinary situations is we add check bits. You can think of it as every code has like a space of codes that are nearby that code. So if you get a flip in one bit, you move to one of these other words in that bubble that the computer will treat as the original word. So you have to add more bits, you know, to be able to encode all those extra words. Well, there's something similar you can do in quantum computing. Kind of one of the more common ways to do it, you end up using to compute, to basically implement one logical qubit. But those individual qubits have to be sufficiently good that the error correction is actually an improvement. Otherwise, the overhead of the error correction will make the quality of the logical qubit worse. So the big announcement there was having qubits that are sufficiently good that error correction works.
May I ask, is this somewhat similar to this idea that I thought people did that in the classical computers?
Mm-hmm.
For each bit they actually have a 3. And then they're all supposed to be the same.
That's triple modular redundancy.
Yeah.
But we actually are smarter than that. And so for 32 qubits, we add log to be able to correct any one error bit. So you end up adding 6 plus 1, 7 bits.
But it's a little bit the same idea, I guess.
It is very similar idea,
yeah.
But you know, but there are differences, and one of the issues is your individual qubit is sufficiently good, or it actually, you know, runs away the wrong direction. You're making a logical qubit that's worse than the original. So cross that threshold, and that gives us the ability to run essentially much bigger programs and trust the output.
This is also just kind of like, this is correcting a qubit with single precision errors. Just what the goal is, right? It's not like,
well, they're kind of analog-ish errors.
errors.
Yeah. So the fidelity, like for instance, when you perform an operation, like you apply a Pauli operator to a qubit, you know, you don't exactly get what you would get, you know, in Mathematica. You know, you get some noise injected in there. So they need the noise to be, for all these kinds of operations, to be lower than a threshold. Yeah. Okay, so I'm talking about something a little bit different than gate-based quantum computing. This is adiabatic quantum computing. And let's see if I can get this done. Why isn't it going down?
Well, you just have to click the mouse on the slide one more time.
Okay, so adiabatic quantum computing. It's based on the adiabatic theorem. So the idea is that you start with some H0 that you know the answer to, right? You know, you can diagonalize it. You know what the ground state is. And, but there's some other H that you really want to know what the ground state is. And so what we do is we form a time-varying Hamiltonian, which is our base Hamiltonian plus some new contribution. Sometimes you'll see it written as like U of t h0 and W of t h1, where one of them will transition slowly down to 0 and the other one will turn on. So by the end of your time evolution, like when t is 1 or whatever you use as your end time, your Hamiltonian is now your final Hamiltonian. And the Adiabatic theorem tells us, subject to maintaining something called a gap, which I'll mention in a moment, that if you do that evolution slowly enough and you start it in an eigenstate, you will track along into the corresponding eigenstate of the final Hamiltonian. So we can use this to get the ground state of complicated Hamiltonians, as long as we can start in the ground state of a simple known Hamiltonian, or solvable Hamiltonian. So some examples I put up here. This is a simple deuteron interaction. And, so this other thing about slowly enough. So what this graph on the right is showing is different evolution times, going from basically what's called the transverse Hamiltonian. That's this H0 in the second line. So you start in the ground state of that, and then you modify that until it turns into a Hamiltonian for a S-channel deuteron mock-up. And then you do the time evolution, and you can see these various lines here. So some of them are evolving too fast, right? The dotted line is evolving in a quite short amount of time, and then you just stretch out the time, and eventually the solid purple line ends up, landing right on top of the deuteron wave function.
Can I ask, because I try to understand what this is. So we say, so the task we have is we have some complicated Hamiltonian. We like to find the ground state, the wave function, let us say.
Yeah.
So, and then we have a simpler system we can easily solve for the ground state wave function. And you can somehow go smoothly from one to the other to the Hamiltonian.
Yeah.
So why do I need all this quantum computing? Why don't I just solve my Schrödinger equation or whatever for the simple one, and then just add this W? I have a little bit different potential. I can easily solve it in a little bit different potential once I have a good guess for the simple potential, and then I can bootstrap my way all the way over there.
Well, you'd be doing an awful lot
of small changes
of conventional computing.
Yeah, conventional
solutions.
Computing.
And let me just point out something. Yeah. If you're doing this, say, on a lattice, and I crank the number of points in the lattice up, I'm running on, say, 1,000 cubed lattice or something. It's a lot of data. And so I want to diagonalize that thing or partially diagonalize it. That's quite expensive.
So this should be this should be cheaper.
Right, and now you're suggesting taking little tiny time steps and resolving and resolving and resolving. It would take forever.
Not exactly time steps, perturbations on the potential.
Right, but
there's no time in what I'm.
Well, there is, because you would advance t, change the mix of the initial.
I'll change W a little bit, and then I'll do another stationary calculation, another one,
That's right.
It's always a little bit different many times. I'll get the same result, right? You're just saying it's not as efficient. Is that what you're saying?
Yeah, it's not as efficient. The whole point of quantum computing is what we're trying to do is get some kind of exponential advantage in the speed of computation or memory or things like that.
But why is it more efficient to have it? Because you also need to represent the wave function.
Exactly. But let me. Okay, then let's say I have 3 qubits. Then I have 8 product states, each of which has an amplitude. Right? If I have 4 qubits, I have 16 product states, each of which has an amplitude. So my number of product states with amplitudes is going up exponentially with the number of qubits. That's essentially where the advantage comes from. That and also entanglement. But you see, on a classical computer, I'd have to have a floating point number for each of those amplitudes.
Yes.
But in a quantum computer, I don't. I have to have log qubits to represent the that number of amplitudes.
Yeah, okay, all right.
Yeah.
So that's where it lies. You can present the classical information more efficiently.
Much more efficient, yeah. Okay, so I just want, this is just.
Sorry, but it's kind of essential to
Yeah,
get this
No,
point.
it's good to get this in place. All right, and as I said, our objective here is to find the ground state of our complicated H. So what I'm going to do here is I'm going to make it discrete over some finite volume periodic space, right? And some problems I'm kind of in, examples, 2D, quantum Hall problem, 3D nuclei. The kind of obvious thing to do is to try and put the shell model on on a quantum computer, but that's actually a complicated coding problem. But maybe just doing a simple lattice, at least I can get the the kinetic energy operator and things like that done in a much more uniform way, and simple maybe better, right? Simple, but just add more qubits and go to a quite large lattice. So the focus actually turns out to be on the Laplacian. And in particular for fermions, the Laplacian is the issue because you can think of the Laplacian operators making connections between neighboring states, and how you represent those states. I mean, this is where it's going to interact with exchange symmetry. So right. So I'm going to just kind of go in some. So I'm going to give some background here because we did I did some earlier work with Ermal and Yantao on the same problem for distinguishable particles. And so there's a paper, there's going to be a reference to it if you're interested in. But key thing is, little mathematical thing is what's called binary reflected gray code. So gray code is a binary code. So notice how I have, this is the number I want to represent, and this thing to the right, that's the code I'm going to use to represent that number. And so you can see it looks like 0, then it's binary 1, and then, oh, why did I use 3? Right? And then back to 2. Well, the reason I'm doing that is the transitions involve a single bit change. So I'm arranging this code so that as you go down the sequence, the transition from one encoding to the next encoding to the next number involves a single bit flip. Okay? And this, you can just keep doing this reflection trick and adding an extra bit, and you can make binary any power of 2 sequence. So that's pretty useful.
So this can be done generally, all number integers all the way up. You can do this.
Yeah, so if I wanted to go up to 256 or 512,
this can always be done.
Yeah, you just keep doing this reflection trick, and then you make the upper block have the new bit will be a 0, and then followed by a 1 for the second half. And then you'll notice it wraps around too. This bit flips, and you end up back at the first. So it's a periodic encoding where you have single bit changes. This may seem like a trivial little detail, but it impacts the operator structure that I'm going to use. So I mentioned we had done distinguishable particles, and so let me go back here for a second. So if I'm looking at these codes, maybe I should point with this for the online people. You can imagine I could have sigma x on the first bit as kind of an operator I would apply. And what would happen is every time you have 2 codes with a difference in the lowest bit, it would it would cause contributions in each direction. Because if you apply sigma x to that state, right, it's going to essentially do an exchange. It's going to exchange a 0 for a 1 in that bit, right? Simple enough. So it's going to make contributions by symmetric contributions between 0 and 1, and between 2 and 3, and between 4 and 5, and between 6 and 7, every other one. So now I could add in sigma x on bit 1, and that will pick up things like 1 to 2 and 5 to 6. Because what I'm going to want in my Laplacian, did I show a picture here? See, I need contributions from the neighbors in the sequence to build my second derivative.
So what is a 0 in your you have a 0 in a bit. What is that? What bit does this correspond to? Spin up?
Yeah, 0 is spin up.
Okay, and 1 is spin down.
1 is spin down. That's just a convention. You can do it either way. But that confused the hell out of me when I first started doing this. Yes. I quite naturally assumed that 1 was spin up.
Yeah, but that's fine.
But it turns out all the literature is the other way.
Yeah, but that's your two states are spin up and spin down, encoded here in 0 and 1.
That's right.
Okay.
That's right. Okay, so if now I have 3 bits, so if I took the sum of sigma x on 0 plus sigma x on 1 plus sigma x on, right? Then I've covered all of the transitions. Unfortunately, I've also connected, instead of just having these neighbor contributions, remember to make the derivative, I need to add, the value of the function to the left to the value of the function to the right and subtract twice the current value of the current cell and then divide by the lattice spacing, right? And that gives me the derivative. So I'm almost there, but the problem is I can look at, say, 0, 1, 1, and down here there's a 1, 1, 1. So unfortunately, I'm getting some extra contributions from sum of sigma x, right? I just sum of sigma x sub I. That's almost the key element of my Laplacian, but it's going to generate some connections further along. Is that a better pen?
Yes.
All right, that would almost do it. So the next step is this thing we call a Hamming distance 2 gray code. So here I'm going to use 4 bits, but I'm going to make an 8-element path using the cursor here. So this is the path, the green is the part I want to be using, those codes. And then the idea is that all of those like jumps where a sigma x might connect me, say, from, okay, let me do this. Sigma x might connect me from 2 to 5, right? Sigma x on bit 2. And I don't want that contribution. So if I do here, all of those extra connections are connections to the side of the path. They go into these areas where I have the red ovals in my graph.
I'm still not getting, so of your previous slides, you have your bits there, your whatever gray code. How is that mapped? I mean, your Laplacian, you need the wave function as x minus delta, x plus delta.
That's right.
X.
So
how is that x and delta, how is that mapped onto this?
Right. So let's look at sigma x on bit 0. It will make a contribution, and let's say we're trying to compute the derivative, the second derivative at position 3.
Oh, so your numbers are the positions here.
Right. The numbers are the actual positions in the position order.
All right. So I'm thinking about a one-dimensional loop there,
right?
Because it's periodic boundary conditions like
that's
this.
right.
Okay.
So 7 then
so
wraps back to 0.
So it's one-dimensional broad.
Yeah.
yeah. But let me first understand the one dimension, right?
Yeah.
And now I want to do a derivative. So suppose I want to do the derivative at 3. I need then the wave function at 2 and at 4, right?
Right. So that's right. And so sigma x on bit 0 will give me a contribution from 2 to 3. And then to get a contribution from 4, I have to find the bit that's different. So
Yeah.
sigma x on bit 2 will give me that
Yes.
contribution.
Oh, yeah, but it also connects to 0. and it
Oh,
also
unfortunately, it connects to a few other places.
Yes.
Okay.
And I don't want those. I want to filter those away.
Now I'm with you. Yes. Okay.
Yeah. So the idea is trying to use this simple operation as the core of the Laplacian, and I'm going to try and filter away the unwanted extras that I'm getting. And so the idea here is that you enlarge the state space, and then you say, I'm going to use a subset of it for my actual physical positions.
Okay.
And I'm going to use the rest as a trash can for those unwanted contributions.
All right.
So that the areas with the little ovals in them are the trash cans. And so if you, for instance, and this is called a Carnot map, which you probably never heard of.
If you point on the screen, we can't see it.
Oh, yeah. This area here, it's Carnot map, and you can see that I'm using that gray code idea here. And so it's 1 bit change to go across this way and 1 bit change to go across this way, including the wraparound. And so if I look at any 2 adjacent squares, I know they differ in exactly 1 code bit.
Okay.
Either both vertically and horizontally, and including wraparounds.
Okay.
So it's got some nice properties that way, and you can use this to help you construct operators that will cover the penalized squares. So the squares like here, here, along the bottom, here and here. What I want to do is I want to use the squares covered by the green line as my actual physical space encoding.
Okay.
And I want everything else, I'm going to take those states and I'm going to add a contribution to the Hamiltonian that's big when you're on these other squares that don't have the green line.
So you want to do the derivatives along the green line, is that?
I'm doing derivatives along the green line. So my argument is if I penalize the squares off of the green line, then sum of sigma x is essentially the Laplacian up to a scaling factor and a constant offset.
So it's like a very steep gradient dependency factor.
Yeah, you make it big enough that you won't be occupying those product states will not be part of any low-lying states in the system. Right? The moment you include one of those, your energy is automatically too high. Okay. So this technique can be used for other things too, and I'm going to use it in the fermion context as well. Here I'm using it to make the Laplacian operator very, very simple, trivial almost. So I can use this as my operator, and then in the background I've added in this penalty. And in the previous paper, one of the keys was showing that you could do this in a recursive decomposition, any number of dimensions, and the cost of the penalty was polynomial in the number of bits. Right? So that was why we could say we had an exponential advantage in the distinguishable particle case.
What's the A10, A32 top left?
Oh, those are just names of the bits. I called the individual qubits A0, 1, 2, 3. So it's four bits. There are 16 cells. I'm going to use half of them for the actual physical space, and half of them are a trash can to basically throw away the unwanted contributions from these sigma x operators.
So if you enlarge your grid, it's still 50-50, or what's the ratio of useful to trash can bits?
It's half.
Always half, independent of the size.
Yeah, it's basically half. Well, yeah, no. Each recursive iteration, you get a factor of half. So the the space grows kind of like 2 to the a over 2, or to the what do you call it, little n over 2, where little n is the number of qubits I'm using for position. So the number of physical lattice points grows exponentially with the number of qubits.
And the garbage lattice point?
It grows roughly the same rate.
Oh.
Yeah, so that was the question, whether it
Yes.
could,
Yeah.
and
So this has, by the way, the problem of creating a path that has, where the path doesn't ever have a section where it's adjacent to itself, is called the snake in a box problem.
Okay.
So if you ever want to look it up, but they have very complicated constructions that get you just a little bit more density. But the advantage of this construction is it's exponential. You get an exponential number of useful sites, and it has a very nice recursive construction for any number of bits. So,
Bottom line, I can throw away half of my qubits, which I buy from Google. I can practically use only the other half.
no, you only throw away, well, per dimension, you only throw away 1 qubit, I think. Or no, is it half? No, yes, yeah, half. I throw away half my qubits.
Exactly.
But by doing that, I get a very simple operator structure.
I'm
for
just,
my Laplacian.
fair enough. I just
Yeah.
want to know the budget.
Yeah.
How much money I have to invest in my quantum computer. Right?
Yeah.
quick question here, anybody wants more of this?
No?
No, good. Yes?
Okay.
Yeah.
All right. So.
No, I'm good. I'm good.
So we're still a little bit in the history part of this. So this is an example of a harmonic oscillator built with this encoding. This is a 1D problem. So we did 32 lattice positions with 8 qubits. And what we show in this graph on the upper right is the first thing we do is we turn the penalty on so that we go from 256 product states that are kind of active, and then we end up with 32 product states, and everything else is suppressed, right? And so, and having done that, we now have the Laplacian operator, right? So now we've gone from just having what's called the transverse state, and now we've ended up in the ground state of the kinetic energy operator. Right? So then the next step is to turn on the potential, right? So that's the sequence. Okay. Yeah. And so you can see here we give kind of time lapse view. So we start out with every product state having a constant small occupation. And then after the penalty's on, it goes to 1 over 32 as the probability of being in those states. And then after we turn on the potential, the ground state of the harmonic oscillator appears. So we just added in the harmonic oscillator potential over time.
So which one is the one with the penalty, the dashed or the full line down there?
The solid line is without the penalty, dash is with the penalty.
Get a bigger wave function?
No, this is the amplitude for
a
given x that you're treating as physical. So, we've squeezed it from being evenly spread over 256 product states to being evenly spread over 32.
Okay.
Yeah, because that the ground state of the transverse operator happens to be very closely
So this is
related.
1 over square root of 22, right? I mean this dashed line, right?
32, yeah.
32 square root, not 32 but square root, because it's the square is the probability. Okay, fine.
Yeah. Right. And so this is the weight function turning on the penalty, and this is the weight function that turns on the potential.
What is S?
I think this is B of S. Oh, S is a parameter that goes from 0 to 1, and 1 means end of time.
B is what?
That's a weight function.
Okay.
We happened in that paper to call it B.
Okay. B like weight. Makes
I
sense.
don't remember quite why. Okay.
Yeah.
So that worked. So now we have to deal with indistinguishable fermions, and here we need the usual Slater determinant to represent a state. So, so there are actually 4 factorial, if I write down this state, there's actually 4 factorial terms that correspond to a product, to an anti-symmetric state. And so we're gonna choose the one where A is less than B is less than C is less than D to represent the anti-symmetric state. And we're gonna trash can the rest with penalty.
What do you mean A less than B?
Well, the positions, like if
position.
so the idea is in any number of dimensions, I can put labels on all the product states, right? And they have some order.
No, A denotes positions, B, C, D.
Yeah, it denotes the label on a position, because if you're in 2D,
Right. No, understood.
Yeah.
That's the label.
You just enumerate it somehow,
you
right?
just enumerate them somehow,
Right.
and we're going to do it in a way that is similar to kind of natural way of looking at it.
Yes,
But when you go to more dimensions, it's okay. So here I have 1D, 2 particles. So I create a penalty. So the idea is particle 1 is in, say, position 4, and say particle 0 is position 1, particle 1 is in position 4. That would be this square. And there's the reverse. That one I'm going to penalize. I'm just going to select one out of the A factorial, where capital A is the number of particles of the states of my hardware to represent the anti-symmetric state. And I also, of course, can't put 2 fermions in the same state, so I'm going to go ahead and penalize the diagonal as well.
So why don't you? I mean, I don't understand why you throw out the exchange. So I have particle 1 in position 4, particle 0 in position 1, and why do you throw out the opposite?
Oh, you mean these darker blue?
No, that is clear, right? But the other one where particle 0 is in 4 and particle 1 is in 4.
Okay, so the actual state is going to be, say, position. Let's make it position 1. See, where do I want to put the particle label? Yeah, I'll make the bottom be the particle number 0. I'll put this one at position 2. Particle 1, I'll put it position 3.
Okay.
And of course, I'd have a minus
exactly,
sign, and
right?
P0 is at 3,
Yes.
P1 is at 2.
Correct.
Right. So that's the state. But what I'm going to do is I'm going to have the state of my hardware that's going to represent this state is going to be the one that is properly ordered.
Yeah, you want the labels to be in the right order.
So I'm going to say on my hardware, these are all product states in my hardware, this whole map. But I'm only going to use the ones in the upper right triangle to represent actual states, right, that all have this form. How many of these do I have?
Yeah, otherwise you double count or whatever.
Yeah, otherwise it'd be double counting. So I'm just going to use, I'm just arbitrarily saying, this is the state in this rectangle that I'm going to use to represent that anti-symmetric state.
It's a label of that properly anti-symmetrized.
Yeah, but where on the quantum computer do I anti-symmetrize? That's where I'm missing this, right? I mean,
this represents that anti-symmetrized state.
Okay, I'll take it for the time being, and let's go.
Yeah. Okay. And if I want to kill off periodicity, I can always just penalize along, an edge. Right. And that can actually cut the hardware requirements down if you do that.
But why do you want to analyze periodicity? Why would you want to?
There are when remember I said the Laplacian, you can think of it as having terms in it that are motions of particles, right? And because those motions, especially when you get to 2D, they can cause a change in, like, when you move to that other state, its label can jump some distance.
Mhm.
And when it jumps, in order to recover a properly ordered state, you have to basically swap some particles.
But
You have to do a little rotation.
What I'm wondering is, so if you cut off periodicity, do you lose translation invariance? Because usually periodicity is associated with.
Yeah, it depends. One thing to realize here is I can make my lattice very large. And so I can solve lots of problems where things go to zero
Okay.
at infinity. So there's no problem with that. But you're correct. And so if I was trying to do lattice QCD on a quantum computer or something like that, I would probably not put that in. But it depends on the problem.
Well, I guess maybe the other way to ask the question to what you said is how, like, if you want to make the universe big enough such that it's zero at the boundary,
Yeah,
that's more expensive than if you use a smaller periodic lattice. But then you have to trade off.
I have a quantum computer.
Well,
I
then you
can
have to trade
double
off
the
in
size with 1 qubit, you know, or maybe 2 qubits in each direction.
Mhm. Mhm.
Okay. So when I start out here, you can see all these little arrows, the bidirectional arrows, those are the actions of these sigma x operators. They're making contributions to neighbors. And now I've overlaid these penalties. And so if I take my distinguishable particle Laplacian and I layer it on here, then I automatically get all of these, you know, white square to white square contributions. I don't really want these ones that go from white square to penalized square, but it's penalized, so no problem. It'll throw those away. But I'm now missing these red dashed lines because what's happened here is you've moved, say, in a periodic way, right? You've gone from position 3 back to position 0, and now you need to swap the two particles, right, to find the correct neighbor self. Because if I'd gone off the top, I'd end up down here, right, in this square. So what I really need to do is end up over here.
What is red on that figure?
The red, okay, so what I'm trying to do is compare the original distinguishable particle Laplacian to what I need for fermions.
Right.
So with fermions, I added in the penalty, but I'll point out I get lots of connections here or contributions that are correct.
Yeah,
For
but,
fermions.
but you have something called red, and my eyes maybe it's
so-
poor, but everything is black and
Yeah.
white there.
Yeah,
Seems to
well,
me.
I added them. I wanted to highlight them. The point is, if you started in this square,
Yeah.
and you say, I'm making a contribution where I change, which bit? When I change the upper bit here, I'm going to wrap back to this square.
Yeah.
But I don't want to be in that square. That's a penalized square. That's an improperly ordered
Right.
label.
Right.
So I have to instead find a way to deliver that contribution to this square. And that's tracing that red dashed line.
Which line is
There's
it?
very
The red
thin
line.
red lines.
Is it not too visible?
Oh,
It's-
those, okay.
Oh, this.
See,
Ah,
I'm
okay.
off the top
Never mind.
to
That's all
here,
I wanted to know why there's a
but I
red
want to
line.
go
Now
to
I
the
see it.
symmetric position over here.
Yeah, now I see
Yeah.
it. Okay, thank you.
Okay. Right, so how do we implement the red contributions? Oh, wait a minute. Did I get these out of order? I did. Okay, so hold that thought. I'm going to build some technology, then I'm going to do it. So one of the things I needed to do here is to have the same information represented twice in two different ways. And the representation information affects the operators, the operator structure I'm going to use. So if I can, sometimes you want to encode information one way to compute function 1, and you want it encoded another way so that you can compute function 2. And so the idea is, can I just do both? And so I had this idea of what I'm calling here an entanglement gadget. And the idea is I can basically have a penalty when the two encodings don't agree, where the information that's stored in there is not in sync, there's a penalty. And that's really all that's going on. You create a projector for conflict and add a penalty, and then off you go. As long as you start in a state that satisfies it, and you time evolve from there slowly, it will just stay. They will just stay representing the same information. And I use that for gray code and binary, because if you remember, I said I needed to implement this A less than B less than C less than D. Well, it turns out less than on gray code is a pain in the ass, but it's pretty simple in binary. But I want the gray code for the Laplacian because it's simple, right? So what I'm doing here is I'm showing how I can build a projector that tells me when things are, well, first, this is what I need to do is create this unordered projector that tells me that I've picked the wrong representative for a state. So I want to penalize product states that don't correspond to anti-symmetrized states. So let's go. So if I write down codes, these would be binary codes for 0 through 7, the binary column here. And then this is the corresponding gray code. And it turns out you can write down a Boolean relationship between the bits in the two. And you can enforce it kind of bit by bit. So for the I and ith bit, right? So starting if I was 0, it would be the bottom bits and 1 up in the binary. You can compute these projectors. This notation should define it somewhere, I guess, means basically these 3 bits have that value. So it's just projecting one product state for those 3 bits. You build it out of sigma z's. So in any case, you write down this little term, and it locks the gray code bits to the corresponding binary bits. So
then you only need to write the Laplacian in the gray code.
I write Laplacian in gray code, and I write comparators in binary.
And this locks
the
binary code.
Yeah.
Wave. Okay.
Yeah. And as time evolves, if the binary didn't track the gray, right? If you add something in your Hamiltonian that says, oh, we don't want to be in one of those penalized states because it's not a true anti-symmetric state, well, then the other code, the gray code, will go along with it. It has to.
So you're adding this penalty in binary code.
Yes, this penalty in binary code because I know I have a quite straightforward way of implementing less than on binary.
So it's like a potential in these dual spaces.
Yeah, probably it's the same information,
Yeah.
but just with different representations. So the nice thing here is I can pick,
Okay,
I don't have to stick to one representation of the information.
It's just interesting because it's like now the potential in some weird product space where it's different in the 2 different implementations. Like in a gray code, you have the real potential you're interested in. The binary code, you only have this penalty potential. It's killing these.
Well, in the gray code, I have the Hamming-distance 2 penalty, and in the binary code, I have the anti-symmetry penalty.
Yeah, it's just weird. But like in the gray code, the actual potential, the physical potential is essentially, it doesn't exist, it's a one. I'm thinking it's a product of gray code and binary.
It's the same information.
I know.
Yeah. Okay. So maybe to save some time, so I do the same kind of bit level stuff to make the less than operator, and then next I'm going to move on to is I need another thing called rotation operators. So we can start with a simple swap operator. You may be familiar with this, right? That you can write an exchange, like if you want to exchange the information 2 qubits, this operator will do that. And I'm going to need that when, like when I go, say, off the top of my little diagram, and I had to go.
Well, see, this is just the dot product between sigma 0 and sigma 1, right?
That's the units.
Yeah. Yes. And then, so for 2 qubits, if I'm doing a rotation, it's just a swap, obviously. And it doesn't matter which way you're rotating, it's the same as a swap. But if I go to 3, then I can decompose it into products of swap operators. Actually, 2 different products. There's some rules you can use for this.
I'm a little bit confused. So, I mean, this operator there, first you have I0 times I1. These are just the units operators, right, for 1 and 0 and 1. And then the next one is really sigma vector dot sigma vector.
Yeah, the whole.
Right. That one you could write as sigma z times sigma z plus sigma plus times sigma minus times sigma.
Oh,
plus.
there are many ways to write
But
it.
is
Yes.
it those that do the swapping with sigma plus, sigma minus? Is that the swapping where it lies over what?
Well,
because
I think it's the swap operator. You could look at what the swap operator is, just like in a
what
table.
does it do? What does it swaps the 2 things somehow?
Well, if I wrote down the product states, and I had 0, 0, 0, 1, 1, 0, 1, 1, right? This operator maps this to 0, 0, 1, 0, 0, 1, 1, 1. So this would be the information in one of the bits. This is bit 0, bit 1, and then you're going to end up bit 1, bit 0. So it exchange, these 2 product states get swapped. That's what happens.
Yeah.
But you can think of it as this column gets swapped to that column as well.
Yeah. I believe you.
Yeah.
I thought a simple way to understand that is that it's sigma plus times sigma minus, essentially, this operator. But maybe that's not an easy way to understand it.
Yeah. I don't know, there's a lot of ways to decompose
the plus
it.
lifts you up and then the minus you down, then it's kind of swaps.
Yeah, you can probably build it that way. Yeah. So once you've built that, now, if I have 3 particles and one of them, say, had a high label and it wrapped and now has a label at the beginning of the list, then I have to rotate the 3 particles. Like if I have, say, 0, 2, 7. Say I have 3 particles and they're in these positions, 0, 2, and 7. And 0, because of the Laplacian, moves, actually, make that 6, so I have room for it. So let's say I have 8 positions. So this could turn into 7, 2, 6, right? The sigma x, right, because of the gray code, 1 bit flip takes me to here. And now I look at that and say, oh, that's not properly ordered, so that's in the penalized part of my space. So I really want this to go to, I need to map that to 2, 6, 7, and you'll notice that's actually just a rotate. Right. So then what I'm doing here is showing how you can decompose rotation operators as products of other rotation operators. Like this is a fun one, 7 bits rotated, you can turn it into kind of well, that's a trivial case, but I think maybe I have a typo there.
There's an index missing, I guess.
Something went wrong there. right? 3, 4, 5, 6, 6. Oh, no, that's right. This is an identity. So, right. So this is an identity. So the idea is you can rotate subpartitions and then rotate one of the edges of the subpartitions, and then it gives you the full rotation. And so then, well, how are we going to build these things? So they get expensive. When you start like taking products of these things, you start getting big sums of large terms. So that's nasty. So I was looking for a way to decompose them. So there's, I don't know how much time I've got. Oh man,
5 minutes. 7 minutes.
Oh, show us how quantum
if there's
computing is
another
faster.
time slot, I could finish this
It's
presentation.
supposed to be fast.
Okay, maybe I'll skip this. It's fun. Let's see. It's more than fun. It's kind of important. Okay, so the Bloch-Horowitz equation is effective theory in quantum mechanics. So one way to think about it. So the thing you're trying to do is to make a Hamiltonian that lives in a subspace or your full Hilbert space, has the same eigenvalues, and the eigenstates are projections of the original eigenstates. So I can, this first line is P plus Q is 1. P is the subspace, Q is the complement. So I'm just inserting 1 there. That's traditional in quantum mechanics, or QFT as well. Then just reorganize slightly, multiply by the inverse of that operator. And now I've got, in this line, I've got an operator that acts on the projected wave function and gives me back the full wave function. You might think, oh, that doesn't make a lot of sense. You threw information away and it magically comes back. Well, it turns out you have to inject boundary conditions. Like, for instance, you would build a Green's function for this operator, the boundary conditions, regular at the origin, for instance, matches phase shift at infinity. That turns out to be the missing information. And so with that, this in fact does recover the full wave function from the projection, which is a cool trick.
Question, projection is what you need to go from your what was it called, your gray to the binary?
No,
or you just in general?
there are projection operators all over the place, but here the projection operators, the notion of it is you have a complete Hilbert space, and then you have some subspace where you want to build an effective Hamiltonian. So for example, it might be, you have your UV Hamiltonian, and I want to put it in say an 8 quanta harmonic oscillator space, and build an effective Hamiltonian in that space that reproduces low-lying behavior. So that's what the projector would be for this. So this would take these the wave function of the harmonic oscillator, and it would project it down to the overlap with, say, a first few harmonic oscillator states. And then I build this Green's function and apply it, and I get back the original wave function. So now, since it's the original wave function, I can simply apply h to it right here. Right? It's the full wave function. So since these are eigenstates, I'll just get the energy, right, of the eigenstate, and I'll get the eigenstate. And then I project it again, and that gives me this thing on the left. So you notice I have an operator that acts on a projected wave function, and it gives me the energy times that projected wave function. Is that making sense? Yeah. So this is the Bloch-Horowitz effective Hamiltonian. All right. So what I wanted to use this for is for composing or taking a composition of rotation operators. Let's say I have, say a 5-qubit rotation and I wanted to hit it with another rotation operator. So the idea is, well, I'm going to illustrate it here with something smaller, just a swap operator. I'm going to build, I'm going to enlarge my Hilbert space, and I'm going to essentially have my two swap operators that I'm going to take the product of act in subspaces. You can see this A bit. So I'm going to have an extra space that is identified with the value of that A qubit. And my products are going to happen there. So the idea is I make my UV Hamiltonian live in this augmented space. And then I say, how does this behave in the space without A, right? If I trim down to A equals 0. So if I do that and I just basically run the Bloch-Horowitz equation, I get all kinds of cancellations, it turns out, because you'll end up with the Q and P product, right? Q says you're in the excluded space and P says you're in the included space. And when you take the product of those two, you get 0. So that's what I'm doing here. I'm canceling out all the terms where that happened. And I end up with this product. And I get my original Hamiltonian that lived in the low-lying space, plus I end up with the product. It's essentially sequencing through these two pieces of the UV Hamiltonian. I think I made a bit of a jumble of that explaining it, but okay. But the key notion here is that in your low-lying model space, I can get products of functions, right, without ever having to multiply them out and make a giant sum of products. Okay, so if I use that, I can write down an expression that uses that a lot to, for instance, build all possible rotations of 3 neighboring particles.
So you go back, sorry.
Yeah.
Do I understand correctly? The last line, you would not want to write the x01, x12 as you get bigger and bigger because that becomes expensive.
This thing would blow up on you.
And so instead what you're doing is you're constructing it with this Bloch-Horowitz equation that effectively builds that for you, but then you only have single rotation operators of Bloch-Horowitz. The one over the denominator. Yeah. Okay.
Yes. So you can use more of these ancillary qubits to give you more and more little subspaces, and you can sequence through them to take products of things. So you can build quite complicated circuits that way, or quite complicated.
And then you're just relying on the orthogonality of the Q and the P space to automatically kill all the things you don't.
Right.
Okay.
Right. Okay.
And it doesn't really require the dynamics associated with extra space to somehow be heavy. It's not an effective theory in that sense. It's not like some high energy mode. You're just saying, here's a trick I've learned from.
Yeah.
Okay.
That's right. I'm just using a trick I learned about Bloch-Horowitz equation to do these products.
Okay, great.
So then if you write it out this way, you'll end up getting similar things. These plus operators they're basically turning on the A bit or turning off the A bit if it's a minus. And something's funny there. Oh yeah, here are the minuses. Yeah. So if you apply the Bloch-Horowitz equation to this, it will generate all the possible products of the swap operators. Some of 2 and swap 5 and 6, and that will take you to a penalized state, so it's trash canned. So I'm using that technique too at the same time. But all the non-trash canned results of this generate all of the, rotate 0, 1, 2, rotate 1, 2, 3, rotate, 2, 3, 4. And left and right rotations. You need both because particle motions can go off the top or go off the bottom. Right? Or, yeah, something like that. Okay, so now I'm back to those little dashed lines here. So this is making a really simple example. So I take my distinguishable particle Laplacian, I apply it to state 1, 3. 1, 3, that's this guy. And it's going to generate contributions to all sides. This one will, of course, wrap. That's here. Right? So the red one's one I don't want, and I want 0, 1 instead. So then if I take my distinguishable particle Laplacian and I augment it with that expression, a simple version of the expression from the previous slide, it will generate like a bunch of extra contributions. The red ones are, of course, all going into the penalized states. But now if you look at all of the black ones, they're exactly the 4 I need. This is the basic technique, is to build these, basically the repair of the particle order.
I see a minus in front of the last term. Yeah, but there's a plus in front of it. On the
Yeah,
top line.
because and this happens automatically, but if one of the particles goes off the end and wraps, and now the particle order is wrong, when you do the rotation, there's an exchange, and you pick up a minus sign when you exchange 2 fermions. So it just happens automatically. So I'm going to go a little faster here. What was I going to say? Yeah, so this is just giving, I think, the example I gave here, where I had 5, 7, 8, and 5. You can see one of the sigma x's, makes a contribution to 9. So now you have a state 7, 8, 9. Well, you'd like to have 7, 8, 9, but you have, what do you have? Oh, you have 9, 7, 8, and you have to turn it into that. Yeah. Okay. So this is something I'm working on right now, and I need to come up with a formal proof of this. But if I increase my n, let's say I make it very fine-grained, I'll have states that look like this, where I have only a small number of particles in a row. It turns out the number of particles in a row tells you how large your rotation operators need to be to always recover proper ordering. So if I could, so the notion here is that as I coarse grain, then I end up with more and more particles in a row. And I need bigger and bigger rotation operators. So I really want to run it the other way. It's cheap to add more qubits and represent more lattice positions. And when I do that, I'm going to spread things out over rows. And then the question is, am I scaling away the impact of those potential product states where even if it's really fine-grained, I've got some state in here that had, say, 5 electrons in that row. So I think, barring odd symmetries in your potential that cause it to just line stuff up, I think this is going to yield, what I'm trying to say is I can get away with small rotations and never have to do rotations of lots of particles.
Which are more expensive than adding one more qubit.
Oh yeah, much more expensive than adding qubits for the positions. So, I mean, really, this state is a sum of, whoa.
Just pinch it, yeah.
This state at the top is a sum of states like this one on the bottom. And one member of that sum with some weight is going to be something that has all of them lined up maybe. So if I drop that one, does it hurt me? I don't think it does. So, okay, so how am I doing? Oh, I'm close. So I can write out my entire Hamiltonian as I'll use this. I've got the penalty for the Hamming distance to gray code, that's the off the green line penalty. I've got my penalty for unordered states. I could add in the non-periodic thing. I've got my addition to the Hamiltonian to keep my gray codes and my binary codes in sync. What was that? Oh no, this has to do with the comparators. So I have a delta. I have a penalties that go into building the less than operator that I skipped over. And then I've got the kind of core Laplacian with the repair of the particle ordering. And so this B here, if I thought that one row could have all of the electrons, then that would have to be A. And it's still polynomial, but it's just a higher order polynomial that I don't like. So I'd much rather say, oh, B, I could set that to 3, 4, something small like that, and just increase my n to compensate for that. And then little tests, I made a little 2x2, with sort of two-dimensional space with 2 electrons in it, and it's 5 nanometers. I picked the sites, and then my potential is the interaction between the 2 electrons, plus I drop 2 positive charges in, and just let it go. And so and this diagram is showing when I turn on various parts. So I start in that transverse state, and I turn on the penalties for H2GC and ordering, and then there's this swapping stuff that goes in front of the Laplacian. I turn that on, and I turn on the kind of at similar time I turn on the potential, and you can see the ground state running along here. So I tracked all the states and down to minus 4.804, which turns out to be the right. Actually, the simulation took it right there. And I did it 2 ways. One, by just diagonalizing the final Hamiltonian, and the other by adiabatically evolving. And they end up with the same wave function and same energy as promised by the adiabatic theorem. It actually worked. But that means that I must have constructed all of this stuff correctly.
1, 2, 3, and 4 are just excited states.
Those are just some excited states, yeah. So you need the rate at which you can do the evolution is controlled by 1 over the gap to the first excited state. And then this 40,000 was kind of an arbitrary parameter. I would have, well, it turns out it's 25 picoseconds. So you just have to use the right H bar for nanometers, or not nanometers, wait a minute. Oh yeah, electron volts. There. Yeah. And what else? Picture of the ground state, but it's hard to interpret because these are the labels for the positions. So this spot is next to that spot.
Should map back into the.
Yeah, I was thinking about making a density map because then I can overlay the 2 electrons. I probably should do that. And so then I have some conclusions that, hey, it's polynomial cost, so yay. And that means that as I scale my little n up, the number of qubits to represent a position, my cost of my circuit's only going up polynomially, so I'm getting an exponential advantage. And there's some fun things about the entanglement gadgets. Oh, and one other key thing here, since I'm doing finite volume, the gap to the first excited state is protected, right? Which is something you don't get in normal, in infinite volume.
Right.
Yeah, and so that's why I was able to actually evolve in a reasonable amount of time. So that's it.
So these calculations are not on a quantum computer. These are
No,
simulated.
none on the computer in my office at Berkeley.
Yeah, exactly.
Yeah.
You just simulate the thing, right? Okay.
Yeah, it took a little while. It's I wrote a something can use a Dyson expansion. Just
Okay.
So if you get rid of periodic boundary conditions and you lose translation invariance, does the gap become, I mean, the gap is protected by the quantized momentum modes, right?
right, but you even in a non-periodic box you have quantization.
But
Yeah, but then
if
if you
the gap
bound
gets
state, then
smaller,
you're good. Then you have a chance for a gap. If you have scattering states, forget about it, right? Because there's no gap. Then it's then tough.
Mhm.
But so leave it periodic.
Yeah.
That's
If you're worried. Yeah. Okay.
Oh, right, I'm in charge. Any other questions?
Yeah, when is the reservation for?
5:30. So depending if you're on foot or by car or bicycle,
Yeah.
5:30. Yeah, we have 45 minutes to be there. Like we have 10 spare minutes before they cancel the reservation.
So the reservation is on your name, right?
Mhm.
So whoever goes first.
Another important question.
When is the reservation?
5:30
Okay.
for 8 people, and I gather there's at least 1 + 1. So hopefully we can squeeze in a table for 8.
I'm going. Who's going? So what is that? 1, 2, 3, 4, 5,
Oh, and me.
6,
Sorry.
7, 8.
Okay, perfect.
Reservations
See,
for 8.
Oh, and a +1. So we're at 9, right?
All right, you'll find space.
Okay.
Space for one.
Anyway, we'll make it work.
All right.
Fantastic. Okay, thank you.
Thanks.
Yeah.